Hello everyone, in this video we're going to look at the variance and the covariance of random variables. So in chapter 1 we also have the definition of variance and the standard deviation. So now if the it is a x is a random variable, and then we'll also have the variance of a random variable. The definition of a random variable is defined as sigma square equals the expected values of x minus mu square. Well, why do we need to square this? Because if, for example, if I have 2, -2, 3, -3, we know that mean value is 0. We see that you can see that it's up and side and down. It has a change. It has variation. But if you just use the mean value and subtract that, if you don't use that, if you just add the number, subtract the mean value and add together, is going to be 0. So if we square that, we don't have the negative. All the negatives become positive. So we define that the sigma is expectation values of x minus mu, which this is the difference between the x with the mean value, okay, for each x and the mean value. So this the variance, and the positive square root is going to be a standard deviation. The variance is for the discrete variable is x minus mu multiplied with the probability. Okay, if it's continuous, so it's going to be just negative infinity to positive infinity, x minus mu square fx dx. Okay, this is the definition of sigma square, the variance. There's an example here, which is a pretty simple example. X is given, fx is given. What you need to do, just plug all the numbers in. So you just need to plug in. First, find out what is the mu value. Find f mu equals x times fx. Okay, just basically just 1 times 0.3 plus 2 times 2.4 plus 3 times 0.3 equals 2.0. You find the mean value. Okay. Then you add all the numbers. For example, the first one is 1 minus mean value 2 square. You add the difference square and multiply by the probability of the first variable. And plus the second one is 2 minus 2 square times the probability plus 3 minus 2 square, and then multiply by the probability of the 3. Number 3. Okay, so basically add all of them together is going to be this variance. Okay, in the same way you can find the variance for B. Okay, then the variance of a random variable sigma square equals e x square minus mu square. This is from there is a short proof here. It will have sigma square equals, you can see there's 2 mu x times fx, which actually is mu again. Then they cancel with one of the mu square here. The 2 mu square cancel with the last mu square, so it's just the x square. So e expectation value of x square minus mu square. Okay, so this is a simplified version of the previous sigma square equals and x minus mu square. Okay, so this is a simplified version of this one, of the definition. Two examples, which should be pretty simple. If you look at this, if you have a question, just let me know. You please read with these two examples. And next one, we look at the variance of random variable as for x is a function of x. So gx is a function. Instead of doing just a random variable, now we have a function of x. So the variable with the probability distributing the variance of random variable gx is not going to just be x, but is a function of x. Then it's the same thing. Sigma g of x square is defined as all of x gx, which is the function of x. Previously we have x minus mu square, right? Now fx. Now we just use gx minus mu of the gx, which is the mu. Previous we have that, and then multiply by f of gx over fx. Okay, so that's the definition of the variance. If the function of is gx, just replace the x by gx. That's it. It's also pretty straightforward. You look at this example, and it's pretty straightforward. Okay, just have some practice. And also there is another example of the function of gx. Suppose gx equals 4x plus 3. Example 4.12. If gx is a function, then you plug the function into the formula. Use is if it's a continuous function, take the antiderivative, gx and minus gx minus x times f minus mu x times fx. Okay. So there is another definition after the variance. We also have x and y. They may have some correlation. So now we also want to find out the covariance. Okay. Oh, this is not covariance. This is a if x and y be random variables with joint probability, like a two-dimensional function, joint probability distribution fxy, the covariance of xy, so sigma xy equals e x minus u of x times y minus u over y. Okay, and then it equals xy x minus mu x y minus mu of y times f of xy. Okay, this for discrete variable, and a continuous variable, it's it just change that sum into an integral from negative infinity to positive infinity. And this sum, you have two double sum and double integral here. Negative x, negative infinity to positive infinity, x minus mu x, and y times 1 minus y mu y, y minus mu y, and times f of xy, and dx dy. Okay, that's the definition of the covariance of x and y. And also there's another simplified version of covariance. Sigma xy equals e of xy minus mu x times mu of y. There's another example here. You probably can read the example, and it's everything is very straightforward. Find the mu x times gx. Find the mu y times gy. Then find the mu sigma xy covariance. Okay. It's pretty straightforward. From what I see, the example is very straightforward. Just apply the formula. There is a covariance coefficient, correlation of x and y. Okay, if the row xy is defined as sigma xy over sigma x times sigma y. If xy are independent. If xy are independent, then the row will be equals 1. Okay, sorry, equals 0. I think we probably have something like that later. Okay, it should be clear that reader is free of units x and y. The correlation coefficient satisfied inequality. Row xy's coefficient assumes that value of sigma x. It assumes that a value of 0 when sigma xy equals 0. If there is an exactly linear equation, then the coefficient equals 1. And then the correlation coefficient equals -1 is negative. Okay, I believe there is, if they are independent, then you should get a row equals 0. Okay, then you have two more examples. Okay, so let's continue to look at 4.3. 4.3 is as mean and variance of a linear combination of random variables. Basically here you have, instead of doing a variable, but I have a linear combination of variables. So ax plus b, and it equals, the b is a constant, so the value is also b, and it's just ax plus, the expected value of a constant is never changed, so it's always itself. So e over ax, the a is a coefficient, it's just the e of aex plus b. That's why you have this. Okay, so that's pretty straightforward. And if you have gx plus minus hx, is plus minus, it's just the linear operation, plus or minus. Okay, there is one thing you need to pay attention, which is the variance of ax plus b. Okay, if x and b are two independent, the expectation of x and y equals ex times e over y. However, there is one thing you need to pay attention. This is for independent. There's one thing we need to pay attention. Okay, we see that. Let x and y be two independent variables. That's what I said. The sigma of x, y equals 0 if they're independent. There's a variance. Variance you need to pay attention because you have a square. Okay, the sigma is variance of the x plus by plus c. Then the variance of the sigma is going to be a square. Sigma square is, you have to square the coefficient, x square, plus b square and sigma y square, and plus 2ab sigma x and y, the covariance. Okay, this is the only thing you have to pay attention when you have the problem of the combination of x and y for the variance. For the expectation, which is pretty simple, just itself, by plus c, you have a over ex plus a over e, b over ey, just plus c. Because it's a plus minus, for linear for the expectation is much simpler, but for the variance you have to pay attention to the sigma. Sorry, for the square. Okay, that's pretty straightforward. There's nothing please read the examples on the textbook and see if you have any questions. Okay. You see, I think it's not really hard. We're going to look at some examples on your homework and while you do practice. And the 4.4 is Chebyshev theorem. Basically is it means there is the Chebyshev theorem is if you have a large let's just read it. The probability that any random variable x will assume a value within k standard deviation of a mean is that at least 1 minus 1 over k squared. That is probability of mu minus k sigma less than u less than mu plus k sigma. Okay, is bigger than or equal to 1 minus 1 over k squared. Right, so basically, if, for example, let's look at example 4.27. If the mu equals 8, the variance equals 9, standard deviation equals 3. Find the probability of x less than 20, bigger than negative 4. Okay, so we have that. Okay, find that, and we could not exactly find out the probability if we don't have the probability distribution. Now we can estimate approximately what it will be. Okay, so at least it's bigger than or equal to what? For example, if you give it a negative infinity for a positive infinity interval, well, the probability for sure is going to be equals 1 because for sure it's going to be a big. If you give big large interval, you have a better probability, have a big probability. Okay, so negative 4 to 20 is going to be, let's try say if we subtract mu, so let's say how far away it is from the mu value. So the middle one is mu equals 8, and then you have 20 here, so it is 3 sigma. Left side is negative 4, so you also have another 3 sigma. So basically left side you have mu minus 3 sigma, and the right hand side you have mu plus 3 sigma, and you got a k equals 3. Okay, so what do we have is here we can, according to the theorem, it's going to be, we have mu is 8 minus the sigma is 3, so 3 times 4 less than x, 8 plus 4 times 3 is 4 sigma actually, sorry, 4 times 3, the sigma equals 3. So basically I have 4 standard deviation. Okay, suppose this is your standard deviation of 8, you have 4 here, 4 sigma, and another 4 sigma on the other side. Okay, so the probability at least is bigger than or equal to 1 minus 1 over 16, bigger than or equal to 15 over 16. Okay, it's just for another example. If I have, after the first exam, if suppose the average is 80, okay, suppose the average of the test score is 80, then I ask a student to make a, suppose the average is 80 points, okay, the sigma equals 5. So majority people will from 75 to 85 is a normal distribution if it's not, or from the theorem we can just assume, if I ask you What if the probability of a student get a score which is less than 100, bigger than 60? What is the probability that happen? Well, then you can see this is a big interval. Majority of people will get around 80. So we probably get a big percent probability the student will get at least 60 to 100, like in this range. If I give a bigger range, for example, P0 to X less than 100, that's a for sure thing. Okay, because it has to be bigger than or equal to 0, less than or equal to 100. Right, so now your big interval it will be, the bigger probability will be. So now this is what? X is 80 and it's 4 sigma as well again. So 60 to 80, so this is 80, this is 4 sigma. A sigma is 5 to 100. Another sigma, 4 sigma to the left is 60. So it's also 1 minus 1 over 4 squared. That's the Chebyshev theorem. Okay, the whole Chebyshev theorem. It actually is an approximate probability. It does not give you exact probability, but it gives you quick estimation. Okay. In the next video, I'm going to look at the we're going to look at the homework together.